Let's get more practice at working with free-body diagrams by looking at this dock walkway. Now, let's remember here what exactly a free-body diagram is. It's a diagram that represents a body, in this case it's going to be the walkway, that is freed from all restraints. Ultimately, what we remove we have to replace with their static equivalency. And that means that we got three possible kinds of movements that we're going to come back and say, has that been restrained or not been restrained? That means we can have any set of orthogonal translational type forces and then one rotational effect that come when we're looking at this in 2D. Right, so let's go back to the walkway here. We've got this walkway that is an incline of 22 degrees with respect to the horizontal. We have a frictionless roller at A on a horizontal surface, and we have a frictionless roller at B, but notice the surface that it is on and is supporting is actually the inclined plane of the dock walkway. And then we also, it turns out, have this cable here that keeps the dockway from potentially floating away on us and is holding things back in a horizontal kind of fashion. Right? So let's take another closer look. We're going to only go and do the free-body diagram of the dockway. That's what we've got here. Right? Everything has been cut away from the system. Right? Now, I like to do these in a particular order, but not everybody likes that. I like to do it as, let's get the supports in first, but as you're still trying to learn these, maybe it's easier to put the applied forces in. For instance, we know the center of mass of this uniform walkway is going to be halfway along the length. They've indicated to us this symbol G, which is trying to tell us that, okay, you can effectively put that total amount of weight for external static reasons right here at the center of gravity. And that would be equal to m times g. In this case, we'd have 390 kilograms. And then that's the SI system. We got kilograms here. Let's use 9.81 meters per second squared. I would not round that off to 9.8. That means I've introduced air into the system, meaning I only have two significant digits. Now, 9.81 also introduces air because we tend to take this at 9.806 meters per second squared, but that starts to get out to be too many significant digits than I can really support in a general perspective. So I'll tend to use 9.81 in the SI system every single time. Right? And that's going to turn out to be 1,422 and change newtons. That's maybe more than I can really justify, given I only have three significant digits here. Some would say, well, our engineering rule is to use, it starts with the letter number 1, so use 4 even somewhat arbitrarily, or you could just say, well, call that 1.42 kilonewtons. Either one is actually fairly reasonable to specify. I have a bad feeling about that number, and I think I'm thinking of another problem, so you can't see me doing this, but and I don't have my calculator easy for you to see right now, but I have a bad feeling that that's nowhere close to the right number, and of course it's not. Wow, that's pretty bad. That is of course not that number at all. I was thinking of another problem. That's 3,825.9 newtons, and there I for sure would say it makes more sense to call that 3.82 kilonewtons. Again, the old scientific rule of thumb is if I'm rounding to an even number and I have a 5 there, it goes to the even, never goes to the odd. Doesn't matter that you got a 59 here, it's that next number is a 2, or sorry, that 5 is associated with an even number or 2. It's arbitrary, but that's the way we do it. Alright, so let's go back. Yeah, we finally got that weight figured out correctly. So now we go back and we look here. Another easy one is we've got this hold back cable here at B. It's aligned horizontal, so I cut the cable. It is a restraint, and it's preventing displacements in the X direction. That's one of its sole responsibilities. So we got W, we got T. Now we go to the frictionless roller at A. That is more than just friction in the no friction in the pin. It also means no friction on the surface. And that means that there's no restraint horizontally. The only restraint is perpendicular to the surface on which that roller rests, and so that must be only a vertical force, normal to the plane. That's going to be the key, right? Because when we come over to B, that roller is contacting a surface that is inclined, and that means, hey, no friction, then I must represent that only as the normal force at B. Now true, in the global sense, there's an x and y component of that, but it's not an independent set of x and y components. Those two have to resolve themselves so that the normal force at B is at 22 degrees from the vertical, because we have a 22-degree orientation of this inclined plane. Now, big picture here, this is a non-concurrent force system. These four forces do not pass through a common point, so I do have then three equations of equilibrium, three unknowns I could solve for. Now some of you will say, hey, hold on, these two forces are at the same point. Couldn't I resolve that into a single force? And the answer is actually yes, you could. And then I really have three forces. Oh, this gets kind of interesting about what has to happen here, and you can kind of see what's going to happen. Two parallel forces here, there is no intersection point. These two have to resolve themselves ultimately to be a single force that is vertical. And note also what's going to happen here. This sum of forces in the x component of NB has to be equal and opposite to T. Otherwise, because we got no other x forces going on here, and G, that means that, yeah, these two would resolve themselves to ultimately be only a vertical resultant here. That's what eventually will happen when you start applying equilibrium. That's down the road further, but for now, free body diagram standpoint, this is what this model has to be when we don't include friction in any of the rollers here, right? Friction, no friction means no force parallel to the plane. No force parallel to the plane. These two are acting as roller type supports. In this case, literally.